2 months ago, I made a video about a research paper that went viral online, which claimed to have found evidence for an alternate theory of gravity called MOND that doesn't need any dark matter to exist to explain our observations of the universe. But there were a lot of caveats to that claim in that paper by Chae. And now there's a new paper that's come out from Banik and collaborators that has used the same data but a much more rigorous method to analyze it and has claimed the exact opposite thing and ruled out the possibility of MOND completely, and explains why the test done by Chae doesn't give you accurate results. So there is a lot of science drama in this field right now. And those of you who watched my previous video will remember that I gave you a little bit of insider gossip that this paper by Banik and collaborators was coming out very soon, saying, but we will have to wait for that research paper to be published to find out what they've actually found. And of course, once it is published, I'll cover it in a video on this channel. So make sure that you're subscribed and got the bell on so you don't miss out on that one. And here we are now. So in this video, we're going to first quickly recap what actually is the theory of MOND, then move on to what is the test that's done, the wide binary star test. For those of you that either haven't seen my previous video or just need a quick reminder. 3, what previous studies doing this test have actually found. 4, what this new paper by Banik and collaborators is claiming. And 5, their explanation for why that previous paper by Chae wasn't accurate. Before we dive into this though, I just want to say a big thank you to CuriosityStream for sponsoring this video. CuriosityStream is a streaming service that offers award-winning and original documentary films, shows and series that you cannot find anywhere else. With a focus on science, history and technology, CuriosityStream is perfect for anyone who loves to learn. Their documentaries are informative and they're engaging, making it so easy to expand your knowledge on just a huge variety of topics. They quite literally have something for everyone on CuriosityStream. Plus there's new content that drops every single week, so there's always something new to learn, which I love. Now, you're probably here on my channel because you love space as much as I do, so you have to check out the huge amount of space-related content that CuriosityStream has. It just feels like you can endlessly scroll. It's great. I've been loving their series called Breakthrough, which has a whole load of episodes on various different sort of cutting-edge science topics, but I especially liked the episode on the hunt for Martian life by the Perseverance rover. It gripped me from start to finish. So go to curiositystream.com/Dr. Becky, or you can click on that link in the video description below, or you can scan the QR code here to get unlimited access to the world's top documentaries and non-fiction series. Plus, if you use the promo code Dr. Becky, you will save 25% on an annual premium subscription. So thank you so much to CuriosityStream for sponsoring this video. But let's dive in now, first of all, with a recap on what actually is MOND. Well, it stands for Modified Newtonian Dynamics. Essentially taking Newton's equations for gravity, the ones that we all learn in high school, and tweaking them just slightly for objects that have very small accelerations due to gravity. It is classed as an alternate theory of gravity because it is currently not the most widely accepted theory. That falls to Einstein's theory of general relativity, which says that gravity is caused by mass curving space itself. The equations that you use essentially describe how space is curved more for heavier objects, but again, for everyday solar system speeds and masses, general relativity does just reduce down to Newton's equations, and then for heavier objects like black holes is where it starts to differ. General relativity has passed every test that we've thrown at it with flying colours, hence why it is the most accepted theory. But the consequence of general relativity being our best theory of gravity is that it tells us that on much larger scales, the scales of entire galaxies, of trillions of stars, or even clusters of galaxies, is that there is 6 times more matter that we can't see, that doesn't interact with light, than there is normal matter. We call this dark matter. There is a huge amount of evidence that is built up for dark matter over the past century across many different observations. I've made a video on all that evidence before if you want to check it out. But the problem is that particle physicists, in their model of what all the stuff of the universe is made of, don't have anything that dark matter could be made of and haven't managed to detect any of it to work out if it's a brand new particle or what. So a lot of alternate theories of gravity that don't need dark matter on these large scales to explain our observations of the universe have popped up over the past couple of decades. Again, I've made a video on this before if you want to check that out. But probably the most well-known of all of these alternate theories is MOND, which was first published in 1983 by Milgram, and has since spawned many different variations of the theory as well. Essentially, the main difference between MOND and either Newton's equations of gravity or general relativity is that it makes a slight tweak to its equations for gravity for very low accelerations. Like the accelerations that, for example, stars on the far edges of galaxies that don't orbit at the speed that general relativity predicts, but that MOND can explain. There's been many successes like that for MOND over the past couple of decades as it's been developed as a theory, but there's also been a lot of failures as well. And if you want a complete review of all of those successes and failures, then I highly recommend this fantastic review paper by Banik and Chae from last year, 2022, that I'll link in the video description down below. So people are always looking for new ways to test our theories of gravity, including MOND. And the one that's been getting all of the attention lately is what's known as the wide binary test. Essentially observing pairs of stars that are orbiting each other at such large, wide distances that the accelerations are very low, and you can test this regime where MOND tweaks the equations. So if MOND is the correct theory, then the speed, the velocity that the stars orbit each other around will be different than what Newton's theory of gravity and general relativity predict. And what's really key about this test and why people are so excited is that you test it at these scales, but it's also applicable to galaxy-wide scales as well, not just like the distances between stars. Now, this test was first proposed back in 2012 by Hernandez, Jimenez, and Allen. And all you do is plot how far the stars are apart from each other on the x-axis here, and then the speed they're orbiting around each other on the y-axis. And if general relativity or Newton's equations are the right theory of gravity, you should get this diagonal line like this. But if MOND is right, then at these wide separations, this should diverge where you get these lower accelerations. The problem is having data accurate enough to actually do this, because you don't directly observe how fast the stars are moving around each other. All you observe is how fast the two individual stars are moving relative to you. So forwards and backwards, left and right, and up and down. First thing you have to do is take out the solar system's movement from those velocities as well, and then you can use them to model how fast you think the stars are orbiting each other. The problem is you don't know how inclined those two pairs of stars are to you, and then also you don't know how eccentric the orbit is either. So it won't be a perfect circle, it will be slightly oval-shaped, but you don't know how oval-shaped, which is why you get such a huge scatter in your data points. And you can see the data was particularly bad in 2012 and in short supply. But now we have the Gaia mission, which was launched back in 2013. It's hanging out at L2, keeping the James Webb Space Telescope company about 1.5 million kilometers away from Earth, which has been observing the precise positions, velocities, colors, brightnesses of over 1 billion stars in the Milky Way, going back to each star 70 times to monitor how all those properties have changed. So now we actually have the data that we need to do this test, now that all of the binary star systems have been identified in the Gaia data. But of course, you still have all of those uncertainties on inclination and eccentricity that give you all of that scatter in your data. So this is why lots of works have started popping up with results from this test in the past 2 years. All using the same Gaia data, but all finding completely different results. Some in favour of Newtonian gravity and some in favour of MOND. Essentially, the field is a bit of a mess. Now, the Chae paper made headlines earlier this year because they claim to have found incredibly strong evidence in favour of MOND, 10 sigma. That translates as a 1 in 10,000 trillion chance that their result was actually just a statistical fluke. They're very confident in their result. They claim that from this diagram, which again shows the separation against the orbital velocity, with all of this scatter on the individual wide binary pairs that they're testing, if they binned that data and said, okay, take all of the stars at this separation and let's work out the average and do that in these bins, and they get these average points that are joined together by this line here, then they could see this deviation away from what Newtonian gravity predicts and instead matches what MOND predicts. Comparing scatter points to lines is not exactly the most rigorous way to test this though. Like, the proper way to do this would be to use something known as Bayesian statistics. Essentially, it's a way of saying how likely is something given that I already know something else. So for example, if I roll a die 100 times, I then want to know how likely is it that that die is biased, that it's weighted in some way if I already know that I have rolled a 6 40 out of 100 times. What you essentially get is like a probability distribution for whatever model parameter that you care about. So you can say, how likely is it that my model parameter is this value versus this value? How likely is it that my theory of gravity is Newtonian versus MOND? That is what Banik and collaborators have done in the paper that they released this month. Fitting the Gaia data using Bayesian statistics to find the most likely theory of gravity that fits the binary stars' orbits. Not only that, Banik and collaborators were incredibly rigorous with the data that they used from Gaia. They imposed lots of quality cuts on it to ensure that the data that they were using was only of the highest quality to be able to do this wide binary test. So what Banik and collaborators did here that was really clever is they introduced this new parameter in the model to try and quantify the different theories of gravity that they called alpha grav. So they calculated what the velocities would be in a load of simulated pairs of stars, so of various different inclinations and different eccentricities, so that they could then model, okay, if I use Newtonian gravity, what orbital velocities do I get? And if I use MOND as my theory of gravity, what orbital velocities do I get? And then they can say, okay, this is now how orbital velocity relates to separation for all these different inclinations and eccentricities. And they said, okay, when the orbital velocities are the values that we expect from Newtonian gravity, then alpha grav will equal 0. And when the orbital velocities are what we'd expect for MOND, then alpha grav equals 1. That way, the model and the Bayesian statistics that they use could interpolate between any value of alpha grav. It didn't have to equal 0, 1. It could be less than 0, somewhere between 0 and 1. It could be greater than 1 in the case where perhaps neither Newtonian gravity or MOND are the right theory. And that is really crucial because it takes away that element of like a human bias in the science. It allows the model to follow the data and you're not biased by whatever result you expect to get, that you think that you should get. And of course, it then folds in all those uncertainties on the inclination, the eccentricity that cause so much scatter in your data as well. So Banik and collaborators tested their model with 8,611 wide binary stars from Gaia. And for those familiar, they use Markov chain Monte Carlo methods to get at the probability distributions for alpha grav and also all the other model parameters that they have and how the uncertainties are correlated. For those not familiar, just focus on this panel of the plot, where you can see this distribution for the most likely value of alpha grav for the binary star data they have. And you can see the probability is highest around the 0 mark, i.e. Newtonian gravity, not MOND. The exact value they quote is minus 0.021 with uncertainties of plus 0.065 and minus 0.045, which excludes MOND to such an extreme confidence of 16 sigma, or a 1 in 100,000 trillion chance that their result is just a statistical fluke. It's a really strong result. And they even tried to tweak the model parameters to see how far you would have to change things to even get alpha grav close to 1 and to matching what MOND predicts. But the highest that they could get it to go was only 0.15. The only way that they could get their model to agree that the data matched what MOND should predict is by tweaking when that transition to the low acceleration regime happens. But then that would throw off the fits to galaxy rotation curves that first motivated the need for MOND in the first place. With the claim of such a strong result though, which was the exact opposite of the claim of a very strong result that Chae made a few months ago, they had to dive into why these two results using the same data set but with a different method were so different. And this is where it gets interesting. So the Chae study used a sample of 26,000 wide binary stars to do the test, as opposed to the 8,000 or so that Banik and collaborators used. But Banik and collaborators put much more stringent quality cuts on their data, finding unsurprisingly that the biggest impact comes from a quality cut that you put on the velocity of the stars that are measured by Gaia. If you apply this cut to the Chae data, you remove those wide binary pairs with big measurement errors on their velocities, and you shrink the sample by only 20%, but the preference for MOND completely disappears. The dashed lines here are what MOND predicts. In the top panel, you have the full sample and it seems to follow that dashed line, but in the bottom panel, the reduced sample with the data quality cuts go nowhere near that dashed line. So personally, I believe the results presented by Banik and collaborators over the results presented by Chae. The method is more rigorous, the data is more reliable because of all the quality cuts, and every single question I had was answered in the 45 pages of this research paper. It's very thorough. And it has to be. The first author of this paper is Banik, one of the biggest supporters of MOND for a long time, who literally just last year wrote the book on all the evidence for MOND. If he's now first author of a paper that rules out MOND to that level of significance, it does have to have all of the detail. What's interesting, though, is that this is really only a test between MOND and Newtonian gravity, because it's on the scales where Einstein's theory of general relativity reduces to Newton's gravity. It's not a comparison between MOND and then Einstein's theory of general relativity plus dark matter that's happening on much larger scales. So Banik and collaborators point out that you cannot use their results to then argue for the cold dark matter theory of the universe either, which they point out is still complete. And perhaps it might turn out that the best theory of gravity is actually a hybrid one between general relativity and MOND, or some other alternate theory of gravity. But all we know for now, thanks to this research paper, is that the best theory of gravity to explain our observations of the universe definitely isn't MOND. Before we get to the bloopers, I just want to say a big thank you, first of all, to my colleague Harry Desmond, who works in this field and just talked through with me, like, what is the current feeling and status in this field right now? It was so helpful, not just for this video, but also my previous video that I made on this topic. And then secondly, to Banik, the first author on this research paper that's just come out, because they sent me a draft of the research paper before it was published, and that meant that I could prep this video ahead of time, which was so helpful. That's my light slowly falling down from where I have just propped it up against the window. It's like a real shadow here. And that has been observing the precise positions, velocities. What the frig does that say? Colours. It looks like it says blouse. I don't know, I got blouse from colours. Going back to each star, that you should get, and then of course it folds in all those uncertainties in eccentricity. Is that how that happened? Am I glad to be back filming? Yes. Do I still wish that I was in the Maldives? Also